Alright, today I'll be talking about summation. So we're going to find what is the value of the sum of 1 all the way to n is, the sum of all the positive integers from 1 to n is. Actually, this is equals to n over 2 times n plus 1. I'm going to show you a proof for this. So the proof starts off, I'm going to write with Sn equals to 1 plus 2 plus 3 plus dot 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 all the way till n minus 2, n minus 1 plus n. So as you can see, this Sn term here is basically in this 1 plus 2 plus 3 all the way to n is in ascending order. I'm gonna write this in descending order right now. So rearranging the terms, n plus n minus 1 plus n minus 2 plus all the way till 3 plus 2 plus 1. So what I'm going to do now is I'm going to add up all the corresponding terms. So I'm going to add up the first term, the second term, the third term, all the way till the last term. So for the first term, n is going to add with 1, n minus 1 is going to plus 2, and n minus 2 is going to plus 3, n minus 2 is going to plus 3, n minus 1 is going to plus 2, n is going to plus 1. So adding these two number statements up, the left hand side will be 2Sn. So I'm going to sum this whole thing up. So Sn plus Sn is 2Sn. First term, n plus 1 is equals to n plus 1. The second term add up each other, n minus 1 plus 2 is going to give me n plus 1. The third term, n minus 2 plus 3 is going to give me n plus 1, and so on. This also gives me n plus 1. Everything is going to give me n plus 1 actually. In fact, there are n terms of n plus 1. There are n of such terms because there are total of n terms in Sn. 1, 2, 3 all the way to n, n minus 1, n minus 2 all the way to n. Each has n terms. So 2Sn equals to n times n plus 1. And now I'm going to divide both sides by 2. So this is going to give me this. I'm going to show you another proof which uses the telescopic sum. So a telescopic sum is where the subsequent terms cancel out, and this basically leaves behind the first and the last term. So we can look at this formula, I plus 1 square minus I square. We know that this equals to I square plus 2I plus 1 minus I square. The I square will cancel out, leaving us with 2I plus 1. Now I'm going to show you a telescopic sum using summation. I equals 1 n I plus 1 square minus I square. This can be rewritten as, we start off with 1, so when I is 1, 1 plus 1 square minus 1 square, plus when I equals 2, so it will be 2 plus 1 square minus 2 square, and this goes on till n plus 1 square minus n square. And through telescopic sum, we know that in this case, this is 2 square. 2 square will cancel out with this negative 2 square. 3 square will cancel out with the negative 3 square, which is in the next term. So this one will be cancelled out. The negative n square will be cancelled out with the n square that appears before it. Is in front here, within the dots. So what we have left is these two terms. This is a telescopic sum. So the summation of I plus 1 square minus I square is equivalent to n plus 1 whole thing square minus 1. At the same time, we can re-express this equation as this over here. It's the same thing, so I'm gonna write and I equals 1 to I plus 1. Yeah, these two are the same. This and these are the same thing. So I'm going to rewrite it as this plus, which equals to n plus 1 square minus 1, which is also equals to n square plus 2n plus 1 minus 1. These will cancel out, leaving us with this. And for this, our key objective is to find this thing, the summation of I, and from 1 to n. So regarding this second term is this second term is equivalent to n times 1. So I'm going to bring this to the right hand side of the equation. So 2 times I equals summation of I equals to n squared plus 2n minus n, which gives us n squared minus plus n. And I'm going to divide both sides by 2 to get rid of this. So n squared plus n divided by 2, and we get the answer. Yep. And that's all for the proof. I've shown you 2 proofs. I hope you understand how to derive the formula for the summation from 1 to n where they are all positive integers. Thank you for your time.